Hello everyone. I would like to present my project on StateFarm distracted driver detection for the course EEE6152, that is image processing and computer vision. So the motivation for the project is that we want safe road driving, and around 2.5 million accidents in the United States due to distracted driving, 1.6 million of which are due to the use of cell phones while driving, which is a major distraction. And this is another stat that the distracted driving leads to around 3,000 deaths per year. And although the the accidents due to cell phones are mentioned, we are not restricting our project to only cell phone distractions. So, task at hand, basically, what we have to do for detecting a driver who's distracted. So the task is to classify driver activities recorded by 2D dashboard camera, which captures the images of the driver continuously. And then we are going to classify these using machine learning and computer vision techniques. So 10 class labels. And so this can be put forth as a multi-class classification problem. And then here are some of the labels noted down. Safe driving, texting right, talking on the phone, operating the radio, reaching behind, hair and makeup, talking to the passenger, all sorts of activities. And this is the data set is sourced from a competition hosted by StateFarm on Kaggle.com. The data set has 22,424 images, quite a lot of images, which were captured by a 2D dashboard camera. And each image out of the huge number of images is a 640 by 480 image. And just a fun fact that the drivers were not actually driving, but were pretending to drive a towed car. And the data has 10 class labels. And I think that it is a comprehensive list of activities that the drivers do while driving. So, this is what the data looks like. There's one driver driving safely, one operating the phone on the right, one talking on the phone on the right, then there's the same on the left, one's drinking coffee, and then one's doing some hair and makeup, and then there's the last one who's talking to the passenger. So pre-processing. Before we put the image into a machine learning classifier and get the predicted labels, we have to do some pre-processing. Some pre-processing steps which we have to follow are reading the data from the CSV, reading every image. We need to resize the image due to computational constraints and to satisfy those constraints, and creating a numpy array of the images which will be fed to the classifier, and creating one hot encodings of the labels, which is very important, so that the labels are compatible with the neural network output. So our algorithm of choice is neural networks. Two main architectures that we will consider are AlexNet and VGG13. So AlexNet developed by Alex Krzyzewski, VGG13 developed by Visual Geometry Group. AlexNet, to start with, is a simple 8-layer neural network with 5 convolutional layers and 3 fully connected layers, 2 normalization layers which we don't use anymore, 3 pool layers which we keep. Normalization layers not common anymore. So details of the AlexNet are 8 layers, 5 convolutional, 3 fully connected, max pooling layers included, no normalization layers in our case, ReLU activation first proposed by Alex Krzyzewski, and softmax in the last layer, unlike sigmoid, which is used for binary classification. So cost function with the softmax will become categorical cross entropy. Other details of the neural network are 10 raised to minus 5 learning rate, Adam optimizer instead of stochastic gradient descent, 3 by 3 conv filters at stride 1 so that we don't miss out on any detail and get all the features, 2 by 2 max pooling at stride 2, and use of dropout at 25% probability so that we drop some connections randomly and uh, prevent the model from overfitting. And yeah, that's it. And 15 epochs for training. So VGG is a 19-layer neural network developed by The visual geometry group, 16 convolutional layers, 3 fully connected layers, just like the AlexNet, softmax at the end. So some details, we are going to use only the 13 layer one due to computational restrictions and low computing power. 10 convolutional filters of 3 by 3, um, uh, 10 convolutional layers of filters of 3 by 3 size and stride 1, 3 fully connected layers, max pooling layers 2 by 2 and stride 2, and we are going to use zero padding of pad 1 so that we preserve spatial dimensions and do not lose out on any information. Dropout with a probability of 50%. That's what we are going to use. ReLU activation same as AlexNet, and softmax in the last layer for multi-class classification. Atom optimizer, learning rate 10 raised to minus 5, but just for 10 epochs, as this is a 13 convolutional layer, 13 um, layer neural network, so that's why. Results of the AlexNet, we can see that the model loss and model accuracy are pretty exponential with the number of epochs, and model loss decreases exponentially. You can see it's a good graph, but could have been more exponential, and which signifies that the learning rate is somewhere between low learning rate to good learning rate, because the convergence is somewhere between good convergence and slow convergence. Training accuracy is achieved at 95.5% and test accuracy at 96.6%. So the exponential curve here we can see exactly the other way around in accuracy versus epochs. Much worse results for the VGG net, as the model did not learn the function properly. Training accuracy just 10%, test accuracy just 11%, and shows that the learning rate was also bad, and the neural network did not learn the function as a whole. And just to conclude, although CNN is a powerful tool for image classification, it needs a lot of optimization. And CNN with good optimization can get unbeatable classification rates. So that is what we have to keep in mind, that we need to optimize our model, choose good learning rates, choose the number of layers, which is, there's no rule of thumb for choosing the number of layers. It's just how you do it, just how the function, how complex the function is, how well separated the data is. It's that way. And conclusions specifically related to this project are: model was clearly overfitting, and there might be some solution to this, and it was overfitting because we could see the difference between test and train accuracy. So test accuracy was always greater than the training accuracy, and never, even for the from the very first epoch, which is a little towards the overfitting side. And so what we can do is keep driver images together. So say if we have 50 drivers and some images for each driver, then we can set 35 for training and 15 for testing. So something like that would be better, so that the model hasn't seen that driver image earlier, so it does not get to cheat. Using better learning rates. Learning rate is an experimental approach basically to choose the best learning rate. So more experimentation will help in choosing better learning rate. Regularization. So when there's overfitting, we can use a regularization parameter lambda added to the logistic regression cost function of the neural network, and the logistic regression cost function, the weights can be minimized. So L2 regularization is just the sum of squares of all the weights chosen in the neural network is less than some threshold. Uh, so it leads to a diffused curve, and the model uses all of its weights to some extent. And with better optimization, both architectures will give very good results, as they are proven for multi-class classification, and they can lead to amazing results in distracted driver classification also. The overfitting thing is very important, just to conclude, because the convolutional filter is going to convolve with the image, and we need to backpropagate the error or misclassification, and then set the weights of the convolutional filter. So next time uh, extracts the specific information, the specific features related to classifying the uh, image correctly. So these are my references, and mostly based on AlexNet and VGGNet. And that's it for the presentation. And I would like to show you a quick demo of my work. So as we see, I have already created the model in here, and the training was done. And these were the loss functions. These were the graphs which we saw earlier. And just to quickly show you that I have taken a small subset of the test data, and I predict the classes for the test data. And as we can see, we can get these classes from 0 to 9. So it's a 10 class classification. And the actual classes can be shown as well, just that these are in the one hot encoded form. So we can see. So this indicates class 0. So that's class 0, 1, 0, 0. This indicates class 7, 7, because this is 8 and 9. This indicates class 5. So yeah, 5. Most of the predictions are correct, but the problem is just that the model might overfit. That's all. Thank you. Thank you for sparing the time to watch my project. Thank you again.